Now we're going to look at parallel connection for RLC for resistance, inductance and capacitance. And we connect it to an alternating voltage, and what will happen. We have the same rules for the resistance, that there is no phase shift between the current and the voltage, and for the inductance the current is lagging 90 degrees in relationship to the voltage, and for the capacitor the current is leading 90 degrees in relationship to the voltage. And we have the rules RLC and civil to remember what will be first and last of the voltage and current if we got an inductor or a capacitor. So the basic thing is the same. And we know in a parallel connection that the voltage is the same across every component. So actually we can take these vector diagram and put together because they all have the voltage as reference. So we can have vector diagram where we have the voltage for the basic and the current for the resistor this way, the current for the inductor going this way, and the current for the capacitor going this way. And we can move these vectors because they are free. We can move them freely, just they keep the length and the direction. So the current for the inductor we can place out here, and also the current for the capacitor we can place out here, and we can then add the current together and get the total current. For the serial connection we saw that we can make some triangles for the impedance, and I hope you can see that it is not allowed in a parallel connection. You cannot make impedance triangles for a parallel connection. So we just keep on going to the vectors for voltage and current. So for example, for a circuit with a resistor and a capacitor, RC circuit, we have for a parallel connection the voltage is the same, and we have the current for the resistor, and we add the current for the capacitor, and then we have the total current. And we have the phase shift phi because that's the angle between the supply voltage and the total current. If we got a resistor and an inductor, we know that the current for the inductor is lagging 90 degrees in relationship to the voltage, and then we can add the current for the resistor and the current for the inductor and get the total current, and we have the phase shift, and we can see here the total current has a negative angle in relationship to the voltage. And finally we also can have combination of a resistor, capacitor and inductor, and we have the current for the resistor and the current for the capacitor and the current for the inductor, and we add these three vectors and get the total current. And we have a phase shift, and in this situation we have that the current for the inductor is higher than the current for the capacitor, and we get a negative angled current. It could be the other way, that the current for the inductor is lower than the current for the capacitor, and then the total current will be in a positive angle. We can also have a situation where the current for the capacitor and the current for the inductor is equal, and then we can see that the total current and the current for the resistor must be the same. And if we got this situation, we got resonance. So in a parallel connection, if the current for the inductor and current for the capacitor is equal, we have resonance, and these current can only be equal if we have that XL and XC are equal, that the reactance for the components are equal, and then we got resonance like we have in a serial connection, and we can use this formula. we have to remember that this formula is only when we got a perfect parallel connection. It means that we only got components in parallel. We have no serial connection of components. We don't have a mix. And this formula is also working if we got a perfect serial connection. So we have components connected in serial and no parallel connection at all. But we don't have the impedance triangles for the parallel connection, and how can we then calculate the impedance? We know from direct current that we can get the total resistance in a circuit if we have 1 divided by, and then again 1 divided by R1, 1 divided by R2, and 1 divided by R3. Now we just have to remember we have these vectors and that the resistance is in angle of 0 and XL has an angle of 90 degree and XC has an angle of negative 90 degree. So all the reactants XL and XC has an angle of 90 degree plus minus. So the impedance is equal to 1 divided by, and then all the components, 1 divided by resistance, 1 divided by XL, and 1 divided by XC if we got this RCL circuit. And actually 1 divided by R, we know that from direct current that is the same as the conductance. We don't know 1 divided by Z and 1 divided by XL and 1 divided by XC, but you can look in your book chapter 25.2. We have that the admittance, that is Y, that is 1 divided by impedance. G, that was 1 divided by R, that was the conductance. B is called substitutance, and that is 1 divided by X, and if you got is inductive, you have BL for 1 divided by XL, and BC is 1 divided by XC. So the reciprocal of reluctance is substitutance, the reciprocal of resistance is conductance, and the reciprocal of impedance is admittance. So you may use this formula if you wish, but normally I just use this one, and it is also quite easy. But actually it is nearby the same. We just use the conductance for AC circuit, and we can add the conductance for all the components, or call it admittance, when we have a parallel connection in an alternating current system. So remember, normally we just use voltage current vector diagrams and don't make any impedance triangle for a parallel connection, and all the basic rules are the same.